right, so we're going to talk about thermodynamics, and particularly with respect to this exam and this handbook, of course. The laws of thermodynamics, frankly, are not all that interesting. You probably already know them, or at least are familiar with the concepts. If two bodies are in thermal equilibrium with a third body, they're in thermal equilibrium with each other, which is a lot like saying if the temperature of A equals the temperature of B, and the temperature of B equals the temperature of C, then the temperature of A equals the temperature of C. It's not that interesting. First law of thermodynamics says energy can neither be created nor destroyed, but can be converted from one form to another. So you should kind of be able to identify those if you're given a specific question about them, but we'll just kind of get them out of the way because they're not that informative to us for most of what we do. We have some sign conventions that we're going to deal with, as well as, of course, some definition of lots of terms in thermo. In thermodynamics, the sign convention you'll encounter most often is based on a steam turbine, or a boiler, or a steam locomotive, if you like. If you think of a steam engine of some kind, you've got some kind of flame heating up a boiler, so it's putting energy in to that system, and then that steam is routed somewhere, maybe to a piston and a wheel arrangement on a train or whatever, and we get some work out of that system. The energy in equals the energy out minus whatever inefficiencies, which will also account for thermally. So that model, a steam engine or a train or a turbine, establishes our sign convention. Positive heat or positive energy is energy going into the system, and positive work is work coming out of the system. So at times you'll be dealing with reversed cycles or other inputs and other distractions. So you'll see positive work and negative work, positive heat and negative heat, and it's important to kind of have that basis for which direction is which. The most popular format for discovering how much energy is changing hands would be m dot delta, or m delta H, which is the energy content of a system. Or we can say that the energy flow rate, Q dot, is m dot delta H, where the dot is the first derivative. So energy content with respect to time becomes energy flow rate. Of all of the terms identified on about page 143 of the handbook, which is as good a time as any to open up the handbook, I'll give it its own separate window rather than flipping back and forth all class long. Just get that loading. And, oh, that didn't take it long at all. Okay, good. Page 143. So at the beginning of many of these sections, they start defining various terms applicable to the section. And kind of the only thing that are really of interest are C sub P, C sub V, and H. Get this to where it's visible. So we're on page 143, the very first page of thermo. And H equals U plus PV shows up right in the middle there, and then we've got C sub P and C sub V defined below. The rest of these aren't that interesting. Gibbs free energy and Helmholtz free energy are not used as often. They're no less important to the world, they're just not used as often. Whenever you see the term specific, that means a quantity divided by the mass present. So volume divided by the mass is specific volume. And we can compare that, and that's where the term specific heat comes from as well. So even though it's not listed right here on the very first page, you'll see a reference to C sub P, which is heat, and then lowercase c sub P, which is specific heat, both for constant pressure processes.